Hey there, and welcome. Today, we're going to dive into one of the coolest paradoxes in all of physics. It's a single principle that explains both the music you absolutely love and the silence you sometimes desperately need. So, think about this for a second. It sounds completely backward, doesn't it? If you're trying to block out, city traffic or a noisy office, your first thought is definitely not to add more noise to the mix. And yet, that is literally what your noise-canceling headphones are doing. So, what is the secret? What's going on here? Okay, so here's the trick. Inside your headphones, there are these tiny little microphones, and they are constantly listening to the noise around you. Then, a super fast little computer chip creates a brand new sound wave, kind of like an anti-noise, and it beams that into your ears at the exact same time. The question is, how on earth does adding one sound to another result in, well, quiet? To solve this little paradox, we've got to understand the basic physics of how waves act when they run into each other. And you'll see it's a principle that's both incredibly simple and amazingly powerful.
Look, this isn't magic, it's just really, really cool physics. And it all boils down to understanding the main character of our story today, the wave. Once we really get how a wave works, this whole paradox just falls apart.
So, let's rewind and go back to basics. Before we can get into how waves cancel each other out, we need to be totally clear on what a wave is actually doing in the first place. Okay, picture this. You drop a stone into a perfectly still pond. You see those ripples spreading out, right? That's a progressive wave. It's just a disturbance that travels, carrying energy along with it. But, and this is the important part, the water itself isn't actually moving across the pond. The little water molecules are just bobbing up and down, passing the energy from one to the next. So the big takeaway here is that the energy moves forward, but the stuff it's moving through, the particles, they just kind of wiggle in place. For a simple wave, they all move with the same height, which we call amplitude, and at the same speed, which we call frequency. Now, this example is a transverse wave, but believe me, the exact same ideas apply to the sound waves that we're talking about. All right, now we get to the main event. We know what a wave is. But what actually happens when two waves try to be in the same place at the same time? Do they bounce off each other? Do they crash and explode? Well, the real answer is actually way simpler and a whole lot more interesting. They just add up. Seriously, that's it. It's called the principle of superposition. All this really means is that when waves cross paths, you just add their effects together. So if one wave is trying to push a particle up by, say, 5 units, and another wave wants to push it up by 3, the particle just moves up by 8. And if one wave pushes up by 5 and the other pushes down by 3, well, the particle only moves up by 2. It's just simple addition and subtraction. Now, this super simple math leads to two totally different results. On one hand, you've got constructive interference. This happens when the peaks of two waves line up perfectly. They're in sync. They work together and boom, you get a much bigger, more powerful wave. But on the other hand, you have destructive interference. This is when the peak of one wave lines up perfectly with the valley or trough of another. They are perfectly out of sync, and they completely cancel each other out. And in that one perfect moment of cancellation, you get silence. Nothing. And there it is. That's the solution to our mystery. That anti-sound your headphones make is a wave that is a perfect mirror image, perfectly out of phase with the annoying noise coming from outside. The peak of the traffic noise meets the trough of the anti-sound. So, get this, the two sounds are still there. It's not like they've vanished, but because of superposition, they interfere destructively right at your eardrum. They just cancel each other out. You've literally added sound to create silence. The paradox is officially solved. But wait, superposition isn't just a party trick for creating silence. In fact, this very same principle is the secret ingredient behind the rich, beautiful sounds of music. Let's see how that works. Okay, so when you pluck a guitar string, you create something called a stationary wave. It's really just a special case of superposition. It happens when two identical waves are traveling in opposite directions and interfering with each other. It's called stationary because, well, unlike the ripple in a pond, it doesn't look like it's going anywhere. It just seems to vibrate in place. So how does a guitar actually sing? Well, you pluck the string and waves shoot out in both directions. They hit the ends of the guitar where the string is held down, and they reflect right back. Now you've got identical waves moving in opposite directions, the perfect recipe for superposition. This creates that stationary wave, vibrating at a very specific frequency, which we hear as a musical note. But it's the beautiful, complex dance of even higher frequency waves, the harmonics, that gives the guitar its unique, rich sound. Superposition also explains another musical thing you've definitely heard before: beats. You know, when two instruments are trying to tune to the same note and you hear that wah 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 pulsing sound? That's beats. It's just the sound of two waves with slightly different frequencies drifting in and out of sync with each other.
And what's really cool is there's a tiny bit of math to this, but don't worry, it's super simple. The number of wahs you hear per second is just the difference between the two frequencies. So if one instrument is playing at 440 hertz and the other is at 442, you're going to hear two beats every second. This is exactly how musicians tune up. They just listen and adjust their instrument until the beats disappear, which means the frequencies are finally identical.
So we've seen how this one elegant principle, wave superposition, can create both total silence and beautiful music. But honestly, its impact goes way, way beyond just what we can hear. This principle is absolutely fundamental to so many technologies we rely on. I mean, think about Doppler radar. It sends out a wave, which bounces off a plane and comes back. By using superposition to compare the original wave with the reflected one, it can detect these tiny shifts in frequency that tell us exactly how fast that plane is moving. The same idea is at work in sonar tracking submarines and even in medical ultrasounds that measure blood flow inside our own bodies. It's everywhere. So the next time you pop in your noise-canceling headphones or you put on your favorite album, just take a second to remember the invisible dance that's happening all around you. Our world is constantly being shaped by this simple, elegant act of waves adding together and canceling each other out. It really gets you thinking, doesn't it? Wi-Fi signals, radio waves, light itself, they're all waves. Now that you know about superposition, just think about all the unseen interference, both constructive and destructive, that's happening in this very room, right now. What else is being shaped by this principle right under our noses?